Hi guys, this is Nitin, and in this video we are going to discuss about TensorFlow Lite Model Maker. So this is a library by TensorFlow which makes it easy to train different kind of models, whether it is classification model, object detection model, text classification, and a lot of other models. So we're going to discuss about how we can do object detection using this TensorFlow Lite Model Maker library. So to start, I will work inside the Collab notebook. So this is my drive, and I'm going to create a new Collab notebook. Although there are tutorials available online by Google itself, but I'm not going to follow those because they abstract away a lot of things. So we're going to discuss about the part where we do dataset preparation and all those things. So we need to follow it from the scratch. Okay, let me rename the notebook. So it's going to be TFLite Model Maker with object detection task. Alright, so just to give you a brief about it, I am going to pull this Collab notebook, uh, which is available on the TensorFlow documentation site itself. So they take a small subset of data and they train a model using it. So this contains a lot of things that we can wrap our head around, and a lot of things are also hidden that we want to understand, but it's not available. So I'm going to use this notebook as a starter notebook to follow along with the tutorial, but I'm going to do everything manually. So alright, so let's get started. So I'm back to my notebook, and yeah, I think it will work. So the first and foremost thing that we need to do is we need to set up our environment. So I'll just rename this as a markup cell. So environment setup. I guess this does not work like a Jupyter cell, so I'll have to create a new text cell. And yes, alright, so to set up the environment we need to install some libraries, which I'm going to copy from the Collab notebook, uh, which I'm using as a base tutorial. So we need this Lippot audio library that needs to be installed, and then the TFLite Model Maker, OpenCV, PyCoco tools, and also one thing to notice here is we specifically need this version of TensorFlow. So whatever version is which is being installed right now, it is going to uninstall it and then install the newer version. And one more thing that we can take care of is we can go to runtime, we can change the runtime type, and then we can select GPU so that we can train our model on GPUs. Alright, so with that, let's start the notebook, and we can close our session. Alright, so I'm just executing the cell to install the environment. This will take some time. Okay, so this thing is installed now, so I just close the output of this cell, and then we can go to the next one. So the next part is importing the libraries. So I'll also add a title here. Alright, so the library that we require, I'm going to paste that. So we need NumPy, we also need OS, and then this TFLite Model Maker that we just installed, we need to import these particular sum modules, and then we can also check the TensorFlow model, and just to make sure that we have everything in line, we can also check if the GPU is available. So yeah, so we also have the GPU available, so I can just keep it here and then utilize this cell for some other tasks. Okay, so we have our imports ready. Now we can focus on preparing our data set. So in order to get the data set, we need to download it, right? So I have planned to download the VOC dataset, so I'm going to search for it. So Let's see if someone has the instructions to download dataset. Yes, I guess this is the part, so I can use this link to download the dataset. So I'm just going to use duplicate, and we can include a flag called C so that it continues to download if it fails, and then we can say -o so that we can explicitly say with what file name we want to download this thing. So let me execute this thing. It will take some time to download, although the internet on Collab is already very fast, so it won't take much to download. Alright, so we have our dataset downloaded here, and I can move on to extract this dataset, and I can also visualize it. So in the current directory, as you can see, these are tar files, so we need to extract this thing. So and we need the name of the file. So I'm going to run this thing, and this is extracted. So let's refresh, and yes, we have this thing already extracted. So this is the dataset. The JPEG images contain all the images, and the annotation contains all the XML files, which is in the VOC dataset format. So we can move forward, and then so basically for the TFLite Model Maker, the dataset format which we need to use is kind of a CSV file. It also supports VOC format, but that's a little bit tricky, so I'm going to utilize the base format. So if you see this tutorial from TensorFlow blog, they utilize this CSV file, this thing, and basically the CSV file contains all the data that is required. So I'm going to show you example of the file. So basically this is the CSV file that they are using. So the file format is something like this. So the very first column says that to which set this image belongs to, and then there is a link to the image file, and then there is the name of the class for which the annotation is, and then we have the normalized bounding box coordinates for that particular image or object. Now one particular thing to notice here is there are these 3 separated commas. I don't know for what use they are, but they are there, and then in the last they have 2 commas. So we're going to use the same format to prepare our dataset, so to make things easier and to follow along with the tutorial. So we need a way to parse this VOC dataset, right? So let's try to read it. I'm going to search for VOC dataset parse. So I think this should work. So let's try to test it. So we first need to list out the files. So I can do something like this will tell me first 5 files in the directory, and then I can try to read this file to see the contents. Okay, so we get something like this. This is the name of the image, and then we have the bounding boxes, but we also want the object name. So in order to do that, let me just look at the content of the file so that I can decide a better way to parse this thing. Okay, so we have this root element annotation inside which there is a folder, file name, source, a lot of things. But what is more important is the name of the class and then the bounding box. So we are already getting the bounding boxes. The bounding box slash ymin. Okay, let me print the boxes then. And if contains something, I would like to read it. Okay, so going with the text. Alright, so we also get the names. I think I can modify this thing to have something like a dictionary and then, or maybe a list itself, but the list could contain a dictionary, right? So it could be something like name of the class and then its bounding box. So it goes something like this, and I can take out the class name from here. And now let's see how this works. Alright, so now we also get the file name as well as the class name as well as the bounding boxes, so that's kind of sweet. And we also want to have something like the actual size of the image, and why we need that is because we need to normalize these bounding boxes. So instead of saying integer value x, which means 263 in x direction, we need something like number between 0 to 1. It's like percentage, so 23% from x axis. So those are called normalized bounding boxes, and we are going to do that. So in order to generate normalized bounding boxes, we need the height and width of the image. So in order to do that, I need to read the image file. And I can also keep it here so that it becomes easier for us to load the image. Okay, so we have full path of the image, and now what we want to do is we want to read this image, and then we want to have the height and width of the image. So import cv2 there, and then image equals to cv2.imread file name, and then we want height and width. So because image is a RGB image, so it will contain 3 channels, but we are only interested in height and width, so we get this first two elements of the image.shape array. So with that, this should be okay, and I can also confirm this by printing height and width. Yes, so we have it. So now what I need to do is I need to divide the simply the x-axis and y-axis coordinates with their respective height and width. So for example, this y min, so this is something it goes in the y direction of the image. So in order to normalize this according to the resolution of the image, what we can do is we can simply divide the y min coordinate with the height of the image, and similarly x min we can divide it by the width of the image, and y max we can divide by height, x max we can divide by width. So this way it becomes normalized to the image resolution. And now we don't actually need to return the file name because we will already know the image file name, right? So I'll remove this thing from here as well. Alright, so we have this thing, and we can also round this off to, or just leave it, we will not round it off. So now we know a way to parse our XML files, and using this read content method, I'm going to create the CSV files which we will be required. So if you see this notebook here, they uses this CSV file to basically generate the dataset. So in order to do that, I will need to iterate through all the content. So for that, I'm going to import globe. Globe is a library to list out files based on the global expressions or simple Unix expressions, wildcard expressions, right? So globe.globe, we need to list out all the annotations files. So we do it with this. Let's check out the length of the annotation. Alright. So we have 5011 images or annotations files. Alright. And let's just also confirm that we're going in the right direction. So I can do something like ls, and this will give me the exact number of files inside this directory. So that's 5011, and we can also do it for images. So let's see how many images we have. So we have again 5011 images. Alright, so now we can move forward, and how we can think about generating the CSV file. So we need to iterate through these annotations. For and in annotations or we need to read tables, so we can do something like read content from path, and then just break the loop so we can read out the first path. So there we have it. We have these multiple objects. So I think it would also be a good idea if I can just return the path of the image. So I'll also return the file name. That way we don't have to process it again to generate the file path. So we have it here, and then for image, sorry, I'll get it here. So this is the path of the image, and these are all the objects that contain inside that image, and also the bounding boxes are now normalized according to the image resolution. So even if we resize the image, the bounding box will remain same, because it essentially is like in percentages. So whatever the height and width of the image is, we know that 20% x and 40% y. If we go there, we will get the x1 and y1 coordinates. So that's how it works. So image paths and labels we have. I need to now write a CSV file. Alright, so the way I can do that is simply by using the with open voc.csv. I'm going to write it like that, as f, and then for each level I can also enter it on levels. Okay, I need to break this manually. Alright, so we have TV monitor, chair, and then chair in the first annotation file. So this needs to be written to the CSV file. So now I can simply say f.write. We can use f strings here. So if I go back to the actual format, so this is data set. So kind of data set it is. So we can decide it somewhere here, and I can also enumerate so that we can decide on it. So we get the indexes as well. Now dataset fold, I can say. So default I can keep it as train, and for now I'll just write it here. And then we have the path of the image, so image path. And after image path, we have the class name, which I can get it from here. So instead of object, I can say for k comma v, which is basically key value pair, labels dot items. So for now, let's comment this out and print the key way. Okay, so it's a list, and then okay, and this list contains dictionary. Okay, so I can do something like this. All right. So class name and b box equals to this thing. Let's also quickly print it and then verify it's working. Okay, and there is definitely something wrong here that I need to debug. So when I do items, this return dictionary items, but if I try to convert it to list, I get a tuple. So I need to get the 0th item from it. Yeah, and then I get a tuple. Alright, so I can do something like this, and then again class name and b box that I want. Alright, so we have t monitor chair, which is class name and b boxes for each class inside that image. So now I can move forward, and image path is done. We need class name, that's done. And then after class name, we have this x1 y1 x2 y2. Alright, so it's x1, and then it's y1, and then it's x2, and then it's y2. and those things also needs to be extracted. So instead of VOC I can say and then we see that after x1 and y1 we have these 3 commas. So after x1 y1 we can write 3 commas, and at the last we have 2 commas. So I think this is a bug in the TensorFlow TFLite Model Maker itself, because that's how it accepts the CSV file, but it works, so I'm going to just follow it. So before writing anything to the file, let's just also verify. Okay, so we have train and then the full path of the image, then we have the class name, and then we have these bounding boxes. So this is x1, this is y1, this is x2, this is y2. Alright, everything looks fine. So I can write label, and we also need to write the new line so that it does not concatenates everything into a single line. So with that, our CSV should be ready. So I'm going to run this thing and then wait for it to finish. Yeah, and one more thing that needs to be taken care of is this part. So this dataset folder needs to contain train, test, and this one. So one more, it's called validate. Okay, so we need these 3 folders. Okay, so it's like splitting our dataset. So let's first check what is the length of the annotation. So we have 5011 files. All right, so we can do something like first break this thing into 3070. Okay, so 0.7. So we get this number. So if I is less than 70% of the entire data set, we are going to keep it as training data set, and then you can check elif. So if I is greater than 70%, so this could be validate or test, but because we also want to chunk out the validation test set, so we can do it from this remaining 30%. So if I is greater than 70%, however it is less than so what is the remaining part? So we can take out the 30% of the data set by doing this. So we have 1503 images. So if 70% and plus 500 we can do. So if I is greater than 70% and it is less than 70% plus 500, then it could be into the test set. Otherwise dataset fold could be taken as validate. So this is basically like splitting our dataset into 70 and 30%, and then out of those 30%, because it has only 1500 images, so we take 500 images for test set, and the rest remaining one we take it for validation set. So that's how we define this split, and now we can continue to write it to our CSV file. So I'm going to run this block, and I hope it does not fails, and I'm not printing anything here. So we'll quickly get this voc.csv. So I'm going to import pandas and just going to visualize this thing. Or better, we don't need to do it because we can just open it right here. So this thing is finished, and I'm going to open this file right now. Although seems like a heavy file. So we have this train, and okay, all right, it won't show all the files. All right, so we have train, and then we have the path of the image, we have the class name, and then we have these x1 y1 x2 y2. Okay, this looks nice so far. I hope this does not fail in the future, but for now, okay, so we have our CSV file ready. Now I'm going to move forward, and then I'm going to first of all take out the specs for the model that we're going to train. So this model spec, this is something that we imported out here, model spec from the TFLite Model Maker. So we need to have the efficient at light 0 spec, so we get the spec from there. So we get the configuration spec for the model, and then we need to create the data set. So train data, validate data, and test data, all of these we can get from this CSV file which we just created. So let me run this cell and see if it is going to load those files. So this looks good so far, and I know it won't show anything, but I just wanted to confirm that this thing prints out. Alright, so the last step that we have is model training. So I will write model training here, and then so it's simple. To train the model, we are going to invoke this function object.create. This create is actually going to start training for us as well. We need to pass the train data, model spec which we just created. We can use a batch size of 8. We can either choose to train whole model or only some parts ahead of the model, and then we can set out the validation data. So I'm going to execute this function, and it will start training the model. If something goes wrong, then we need to look into it, otherwise it should start training the model. We would be able to see the epochs and all those lost things. Okay, so I guess so far our train data has prepared nicely, and it has started training the model. So one thing that I do not like about TFLite Model Maker is it does not save the model files in between. So unless you have a full training completed, it won't save the model file. So because the file that you're going to save, it is going to be returned by this function to this model variable. So unless this function completes its execution, we won't get the model file. So let's wait for some time and let it train the model, and then we will write it to the disk, and we will try to evaluate it or visualize it. So actually it's going to take a lot of time on Colab because we already have limited memory with a batch size of 8. But once it is trained, I will try to speed up this video and then show you the actual results. Alright, so once the model is trained, we're going to see results something like this. So I'm not sure why it shows -1, but the actual evaluation or detection actually works, so I'm okay with that. And also because we need to take out the class names and everything, so I'm just training it for a single epoch so that I can get something inside this model variable, and then I can use it to get those things. So it's not mandatory, you can just do that. So I'm also going to show you the steps to save the model. So once the model is trained, you can do something like model.export into current directory, and then model.tflite, and no need to specify this export format. Yeah, so if you just execute this line, it will save this model.tflite only when the model is trained. So I'm just training it for a single epoch, but instead of saving the model, I already have a trained model which I'm going to upload it here so that we can move on forward with that. Alright, so I have trained the model for a single epoch and I've already done it so that when we try to access this model variable, there should be some model. It does not matter if it does not have accuracy because we're not going to use this, but we need it. So that's how you train the model, and once you train it for 50 epochs, you'll get something like this, and you can export it to current directory. So I can also show you how it works. So I'll just execute it for now. Alright, so we have this model.tflite already exported, so I'm going to delete it for now because this is only for a single epoch and I already have a model trained, so I'm just going to upload it here. So Collab is not allowing me to actually upload it directly, so for example, if I just drag it here, let's see if it uploads. Yeah, I think it is trying to do that. Alright, so I have uploaded the TFLite file which I have already trained. I will rename it to model.tflite. So basically, if you follow this tutorial, you will end up here. You will have a model.tflite file saved here after this line. So we can move forward and we can discuss about how we can use this TFLite model to run inference on our own images. So there are two ways to infer here. One is directly through the TensorFlow API. So basically, if you click on the show code, they have these options. So I'm just going to copy paste those functions for now. These are helper functions which will allow us to visualize it. So the first one is here, and I want to remove this thing. So we need CV2, we need this image from pillow library, and then this is the model file path. Now this thing is just copy paste, so it basically creates a classes list with value containing this question mark for the number of classes that our model has. So remember I said we need this model variable because we are going to use this model spec.config.num classes to extract the information from the model. If you already know it, we can create these classes, but it becomes handy if you want to just use it. So and then we have this colors for each class. There is a preprocess image function which loads the image and then resizes it and then gives it back into uint8 format. And then we don't need to do this here, or maybe we can do it. So I'm also going to import time, so we will know how much time it takes to infer. And then we have this run odt and raw results function which does exactly what we want. So I'm going to execute this cell to create our helper functions, and now it's time to do the inference. So to do the inference, we need the image files, and how we can get that is simply by checking out the file names inside this directory. So we have this jpeg image set. I can copy this path, and we have somewhere around 5000 images. So in order to inference it, I'm going to use globe so that we can iterate faster, and then we can quickly select file names. Alright, so we have this images list, and then we are also going to need a display function, so which we can get from here to display the images. And then we are also going to need a random so that we can select randomly images and then show it. So with that, we have our images list ready, and then okay, ipython dot. Okay, so we have images list ready, and then what we need to do is we need to load the TFLite model. So in order to load it, we need TensorFlow, and then we're going to create the interpreter for this model path which we wrote here. So model path is model.tflite. So now we have with this interpreter ready. Now we want to detect for multiple images. So for that I already wrote the code, So detection threshold is something I have set to 0.3. So any detection which has a score lower than 0.3 will be ignored, and we're going to detect on 5 images which will be chosen randomly. So this is basically uh, getting a random number from 1 to the number of images that we have, and then we select any random image from that images variable. So and then we use pillow to open it, and then we can resize it to 320 by 320. We can save it to this path /temp/image, because this runout function basically takes a path of the image instead of the image, and then we can display it. So let me execute this function and see if it works. So this takes around 2 seconds or 2000 milliseconds to run the inference, but so far the results looks good. Okay, so we have our inference on 5 images, and you can already see that because it runs on CPU, so it is taking a lot of time to run the inference. So now we're going to take a look at running inference through ONNX. That will allow us to run the inference on over GPU. So forgot to add title here. So this was an inference via TensorFlow, and now we will move forward and we will do inference via ONNX. So I need to create a text block here. So couple of things we need here. First of all, we need to convert the model to ONNX format. So in order to do that, we need this TF to ONNX converter. So we can install it via this command pip install TF to ONNX, and ONNX simplifier. We also need that in order to simplify the ONNX graph that we are going to export. So this will download the ONNX converter for us. And we have it ready, and now we can think about converting the TFLite model, this model, into ONNX format. So in order to do that, we need to use python-m tf to ONNX.export. We can select an offset of 16. Offset basically means the operation set, so that it uses. TFLite path is model.tflite, and then we need to convert into ONNX. So we need to say output is model.ONNX, and let's hope that this thing works out. Okay, so this I guess does not recognize the TF to ONNX that we just installed, so I'm going to give it another try. Alright, so I think it was convert instead of export. So basically now what it's going to do is it will take this TFLite model and then it will convert it to ONNX. So once that is done, one more thing that we can do is we can simplify the ONNX graph so that it will be easier for us to visualize. So there is another tool that we installed here, ONNX simplifier. So we can call this CLI to ONNX sim and then basically pass the path of the ONNX model files. And if I execute this thing, you'll see it simplifies the model file. So I'm going to write everything into a single line, and we have this thing ready. So now what I'm going to do is this ONNX model, I'm going to visualize it. So since I already have it downloaded here, what I will do is I will use Neutron. So it is already installed on my local system, which you can install via this pip install Neutron, and then the model file name that I have on my desktop, it's called ONNX file. So if I go to this link, So by the way, I'm running this thing on localhost. So just to visualize the ONNX model file that we just exported, you can download this file and then you can run through the same instructions. So basically our model takes 320 by 320 input, and it's channel last ordering, so we need to take care of that, and also the batch size is 1. And then if I check out the output of the model, so I'll have to go to the last. It's already a huge graph. So we can see we have 4 outputs here: call 0, call 1, call 2, and call 3. So I will debug how these things are related, how we can utilize it. So in order to run this with ONNX, we need to write some simple boilerplate code. So what I'm going to do is, now I'm going to uninstall this ONNX runtime and then install the GPU runtime, because we want to run this thing via GPU. So the default ONNX runtime that you might have on your system or a collab, this will utilize CPU to run it. So I have uninstalled it and then installed the GPU version of the runtime so that I can utilize GPU for the inference. So with that, we have ONNX runtime GPU installed. So I'm going to do some imports. So we need this ONNX runtime. We are also going to import CV2 numpy, which we have already imported, but in case if you just want to execute this particular cell, we need this import. So alright, so we can define a class efficient at ONNX. So what input we need? We need a model path, and we need threshold, which we can set to 0.3 again. And then we can load the model. So in order to load the model, first of all we need to define a ORT session. ORT basically ONNX runtime session. So self.ORT session equals to ORT.inference session, and then we can give out model path. And one thing that we need to take care of is this provider. So because we want to run it on CPU, so we need to just provide CUDA execution provider, otherwise we could just use CPU here. So with this, we have a ONNX runtime session ready, and then we are also going to need things like input shape information so that we can resize our images accordingly. So input name is something we can get from this ORT session. Input shape is also something that we can get from there, and we don't need to print it here. So we get this input height and input width. So remember, when we visualize this through the neutron graph, so it was channel last ordering. So that means if we take a look at this input shape variable, so the first element is going to be the batch size, second one is going to be height, and third one goes to be width, and the fourth one is going to be the channel. So we need this height and width that we extracted out here, and so we can move forward. And also remember, when we run this inference, we needed this information about classes, right? So we defined it somewhere here, classes. So if I print out this information, I'll do it somewhere around here. So if I print out the classes variable, it should have a list of all the classes that our model contains. So I'm going to just copy it from here and save it inside our class so that we can reference it later. So we have this thing ready now, and we also need colors so that we can better visualize our results. So that's something we can simply copy from there. So we generate the 0 to 255 based random numbers for the number of classes that we have. So with that, we have our basic boilerplate code ready. Now we can move forward, and then we can define the functions to let's say pre-process or post-process our data. So for pre-processing, we need a image. So first of all, we need to get the scale. So I'm going to paste this code right now, and then we can discuss over it how it works, so that way it will save our time. So we have this image as an input. We can take out the original height and width of the image, and then we can resize the image based on the input size that our ONNX model accepts, that we extracted somewhere here. So it will resize the image according to our need, and then we are also calculating the scale, which might be useful later on, so that whatever input size image we give in, when we infer it on a fixed image size, that is 320 by 320, we can use this scale variable to multiply it with the output, so that we can basically get the actual bounding boxes on the entire resolution of the image. Mostly all the ML models or DL models that I have worked with, they have the channel first ordering, so we needed to transpose the image arrays so to keep the channel first, but in this case we don't need it. Neither it uses any custom mean to scale the images, so we don't also need that. So this will work. So with that, we have our pre-process function is ready, and then we can define our run function. This run function is basically going to run the inference. So again, this run function takes in input as image, it pre-processes the image, and we also have this handy time calculation, so that we know how much time it takes for our model to process the image. And we run the ORT image through the ORT session here, and then whatever results that we get out, we store it inside this results list. So for that, we iterate through this count, and then we check if the score is greater than self-thought thresh. Class IDs we can extract out like this, and results, all those things are same. So let's try to first create an instance of this efficient dat. So let's try to create a class of this instance of this efficient dat. It needs the path of the model, so we can say model.ONNX. Threshold is 0.3 that we can leave, so I can say ONNX model is equals to this thing, and then ONNX model dot run, and basically I can pass an image. So we need to load the image first. So image equals to cv2.imread, and let's just choose any random image. So I'm going to ls, let's take our first 5 images. Alright, so I can load this image and then basically run it through the model to see what output it gives. So we get something results like this. We have bounding boxes of the image, which are normalized based on the image resolution. So whatever height and width our image has, we can multiply the bounding boxes with those numbers, and we get the scaled version of the bounding box. With the class name, we have a color for that image, we have scores, so those are going to be greater than 0.3 because we already filtered them out. So now we can write a simple visualization function which can be used to visualize the bounding boxes. So we need image for that and the output from our model. So we can do something like annotated image equals to ONNX model dot visualize, and we want to visualize it on image, and we want to use output variable for that. So this should give us our annotated image. So because our model already gives the scale version of the bounding boxes, so we can just calculate scales on our input image resolution, and then we can iterate on all the objects. So for object and output, the x1, y1 and x2, y2 coordinates could be taken out from the bounding box key, and then we need to scale our bounding boxes according to the actual height and width of the image. So x1 and x2, these needs to be multiplied by the width of the image. So we can do integer and then x1 into scale width, because that will multiply it with the actual width of the image, and we will know that if 20% is the bounding box at x direction, then if we multiply it with the width of the image, we will know that 200 pixels in the left is going to be the x1 coordinate for our image. Same thing we can do for x2, and then for y1 and y2, we need to multiply these things by the height of the image, because we're going to scale according to the height. So this is going to be y1 and this is going to be y2. So with this our scaling is done, and then I can draw the rectangle on the image. So cv2.rectangle image x1 y1 x2 y2 object color and then a width of 2. So this will draw rectangle, and then we can also use this simple one line logic to say where our text is going to be shown in the image, and then we need to prepare labels, so the label which is going to be written on the image. So we can just use formatting here, the class name and the score, and also multiply it by 100, so we get it in percentages. And the final task is to put text. So we take image, we take this label, and then we put it at x1 and y coordinates with the width of 2, and we can return our image. So with this our annotated image should be ready, and I'm going to execute this line now, and this should give our annotated image at least. Okay, so I'm also going to display it here. And remember, because it returns a numpy array, so that needs to be converted to PIL format. So image dot from array, and then annotated images. Let's see how this works. So one thing I think we have already missed is in the pre-processing function, we can convert this image to RGB format, because OpenCV natively operates on BGR format. So when we read the image here, we also need to convert this to RGB format. So this will convert our image to RGB format. That way, typo. So this looks pretty good, and the classes are pretty messed up. I'll have to see if there is something wrong with the actual classes, or if the model is already giving out wrong results. So it says dog to the chairs, that means there is definitely something wrong. So let's try to visualize on a couple of more images. So for that I will go and create a new cell and then do it here. And now instead of reading just a single image, I can infer on multiple images, and then I can randomly choose the images. So this image path, this could be random, so something like we did upon here. So let's try to visualize on multiple images and see what's going on here. Well, it says cow, bird. So definitely there is something wrong with the actual annotation, and I guess because I have loaded a different set of model from what I originally trained, I may need to override these things. So the point where I trained my model, these were the classes, so I'll just replace it for now. but you can continue to use it because you will train it on your own data set. So this way I'll correct the labels and then I can try it again. So I think now this got pretty great results. So boats, person, bird, TV monitor, yes. So far it looks good. So basically now we are able to export our model to ONNX format, and then we use this handy function to override all the requirements that we had, and then we process the output to visualize it. And I think so far it works. And in terms of latency, I think it is only 157 milliseconds. It's like 1.5 seconds per image, but that's what you can expect from Colab. And if you go back and see the inference time for TensorFlow itself, it's like around 2 seconds. So 2416 milliseconds means 2.4 seconds. So you already get a lot of boost while using the ONNX with the CUDA inference engine. So I think that's all for this video. I hope you learned something new techniques to do data processing, or even using the ONNX runtime to run any ONNX model. So basically all these things are custom. You can write your own pre-processing run functions. You can execute them as you want. It's more about experimenting with it, and then you just need to see the shapes and the output that you get from the model, which we did somewhere here. And then basically you can utilize it to write these functions, to iterate through it and then process it, and then basically you can visualize the results. So I think results already looks pretty good, and we can use this model as it is. Alright guys, thank you very much. I hope you enjoyed the video. I'll see you in the next one.